Today we will talk about an statistical test called the chi-square test, and maybe if you took already statistics, you know how to use it very well. It's very easy and is widely used in genetics. So just that you know, this statistical method is used to determine goodness of fit, and what is the goodness of fit is it refers to how close the observed data is to the predicted data from the hypothesis. So let me show you an example. Something that we are going to do in the lab is to compare the expected data to the observed data, and this happens all the time in genetics. So in this case, we show you with plants, yeah. So, but we can also in the lab we are going to use fruit flies. So, and you will see that although sometimes you expect a ratio of 3 to 1, if you go and look for 4 flies, it's very unlikely that you are going to get exactly the 3-1 ratio. You will need, this is a probability, you will need to measure to count maybe hundreds of flies or 1,000 of flies to get something that is very close to this. Yeah. So the observed data will could be slightly different, and to get this perfect ratio, you will need to have a lot of data. So of course, uh, in some cases, the idea is to try to see that if maybe our hypothesis is not correct. So, for example, we will study epistasis, or if you remember in genetic revolution, they thought that they could answer everything with these Mendelian rules, and now we know that sometimes this is not compatible. It's just because the pattern of inheritance is not Mendelian, or at least not a simple Mendelian one. So the chi-square, it allows to test this hypothesis. So remember that the chi-square test does not prove that the hypothesis is correct. It evaluates to what extent the data and the hypothesis have a good fit. Okay, so that is very important that you remember. And this is the general formula. So here you have chi-square. That is, this is the Greek letter, and here you have the observed, here the expected data, and here you have again the expected data. And let's try to solve an exercise that is much easier than explaining it, just the theory. So imagine that you flip the coin 50 times and you get 28 heads and 22 tails. So you ask yourself, okay, is this happen by chance, or there is something wrong with the coin? So this is your observed data, and your expected data will be to get 25 and 25. But of course, it will be very difficult to get 25 and 25 with this such a small low numbers of samples. So chi-square can allow you to answer this question: is is there a problem with the coin, or is just by chance that this happened? And to do that in statistics, we generally have first the null hypothesis, that everything that happened, that there is no significant difference between the observed and expected frequencies. These happen only by chance, or there could be something wrong, that this is the alternative hypothesis, that one of this the one that states that there is a statistically significant relationship between the two variables. So this is one is by chance, and the other one is that there is a significant chance that there is something wrong with the coin. So now we are going to study what is a critical chi-square value, and with this critical chi-square value, you will or accept or reject the null hypothesis. So you will say, yes, I accept the null hypothesis. So the coin, there is a 50-50 chance of getting a head or a tail. You just need to flip the coin more times, and you will get very close to a 50-50 chance. Or you reject the null hypothesis. No, that don't keep doing that. That coin maybe is biased in some way. So I will give you this type of tables. Here you can see the degrees of freedom, and here you can see the probabilities. And you can read more if you haven't take a statistic. You can read this in the textbook in more detail. If you already took a statistics, this will be super easy for you. And I just remind you that these critical values for chi-square are found in this type of tables, and they are sorted by, again, degrees of freedom, this DF, and probability levels. So 0.95, 0.90, and here the one that we want is this p-value of 0.05. Why? Because here you see are the values that you will reject the null hypothesis, here and here. And this is a two-tail for two-tail test. Yeah, you will have these two red regions where you reject the null hypothesis. And so if the values are calculated if your calculated chi-square value is greater than the critical value from the table, you will reject the null hypothesis. So you will see if the value is here, so it's higher than 3.8, so I get a 7. So is likely that the null hypothesis you can reject it. If not, for example, if you get 0.02, you will be here, yeah, because it's lower than 2.8, so you will fail to reject the null hypothesis. Okay, that in other words, that is what you accept, that your genetic theory is about the expect ratio that is correct. So in other words, and we will do it in a second, and if the value is around here, it means that there are 50-50 chances of getting the right value with the coin. So just to remind you, if you already took a statistic, this is a t distribution. Well, you have two tails. In the f distribution, that is the chi-square, you have this asymmetrical distribution, and you only have one tail. So the t-tests have these two tails, and ANOVAs, yeah, the analysis of variance, and the chi-square only have one tail. So that is important for you to remember. So now I'm going to show you how to use the table, and it's very easy. There are 3 steps, yeah, and one table like this will appear on your Moodle test, or you can bring one of these. So again, first thing, the first step is calculate the degrees of freedom. In this case, is 2 minus 1. Why? Because you have heads and tails. You have these two treatments. If you have a homozygous, if you have two alleles, yeah, it will be also 2 minus 2, and you subtract 1. If you have, for example, a genotype that is 10 alleles, it will be 10 minus 1. Okay, so look for the degrees of freedom, and in this case it will be 1 because you have only head and tails. Second step, so here you have to look for the probability, and you want to be 95% sure to reject the null hypothesis. In some cases, depend on how how sure do you want to be. Some of people use 90%, or they want to be 90% sure, or want to be 95%. Here you want to be 95%. If you are super sure, it will be this 99%. So again, so you want to be sure that to reject your hypothesis, and we're going to use 95%. So here, this will be the correct data, and then you can use the critical value. So you use, this is the value. This is why we take 3.841 in this case. Okay, so now let's do the exercise. That is very easy. It's much easier than the theory. So now we have head and tails. So let's compare the expected values. The expected value will be 25 and 25. And now the observed value, if you remember, they were 28 and 22, and you just have to, I recommend you that in the beginning you start recording it like this. Now, if you remember, the formula is here, and now we just have to apply the formula. So let's start with the values of the head. So the probability of getting a head. So the observed value, if you see it here, is 28 in purple, and the expected value is 25. Yeah. Now let's find the probability of getting a tail. You can do it by yourself. I will give you 1 minute. You can stop the video. So here it will be 22. Here it is, the tail, and the expected value will be 25. Very easy. And remember, we're adding these values. So here it will be, and we're adding this value. Remember, if it was a genotype, you will have, for example, 1 allele, 2 alleles, and you can have more alleles. So you will be adding more values, okay? So it will be like, for example, the an allele A, an allele B, an allele C, an allele D. Yeah, so and you will be adding all these values. And now we just solve the problem. So 28 and we subtract 25, it will be 3. And some 22 and we subtract 25 is minus 3. And we just continue with the math, and it will be just very easy. 18 divided into 25 is 0.72. So that is our value, and now we have to compare it using the table as I showed you before. So if you remember, we talked that we have only 1 degree of freedom, and if you have a doubt how we got that, you can go back in the video. We want to be 95% sure, so our value, it will be 3.8. Yeah, so if our value, the one that we calculate with the formula, and doesn't accept the value, we accept the null hypothesis. So if we are here, we accept the null hypothesis. On the other hand, if it exceeds this, if it goes in this black region, we will reject the null hypothesis. And if so, we have 3.8, and the value that we got was lower, so we will accept the null hypothesis. If it was 5, for example, if the value that we calculated was 5, we will reject the null hypothesis, and we will say, okay, the difference was too big, so there was a problem with the coins. In this case, we said, this, it was just because of chance. If you keep flipping the coin, you will get even, you will find that the values will get very close to 50 and 50 between head and tails. So it was pretty easy. Now I'm going to show you other exercises, and you can practice how to do this chi-square. So now we are going to move into the genetics and how we use the chi-square. And why we use this chi-square? Because we love, as we talked in the previous chapter, that the relationship and the between genotype and phenotype was very simple. However, the more that we study, the more that we know that there is an interaction. Yeah, and that this gene interaction can make things more difficult, and we just start getting a lot of phenotypic ratios that they can be explained in different ways. And as we study in genetic evolution, as I said before, we have been trying to look for tests to tell us, okay, is just something that we want to make the data look like this, or is actually a significant a mathematical test that allow us to say, yes, we are confident that this works in this way. So although we love that everything was like Mendel and his monohybrid cross proposed, and we will talk that there could be cases where this is not always work, and we will start first with these easy examples, and then we will move to more difficult problems, and we can compare the observed data that we have here with the again with the or more the expected data that we have here with the observed data that we see in nature, and we will also do it in the lab to try to see how much they fit. And one of the labs will be actually trying to use the chi-square to see what kind of ratio you get. And in humans, these tend to be very complicated, so this is why we use flies to use simple examples to study this. And a simple test that we can do is taking this Punnett square, a test cross that we already know what it is. And the idea is that we should get a ratio of 1 to 1. One that are heterozygous and one that are homozygous recessive. And as you will see in the lab, this is not always the case. It's not always that we get this exact 1 to 1 ratio. So let's start with the a genetic problem. It's slightly different from this one, but that we can apply this chi-square into genetics. So now imagine this question. You go in the field and you look for these flowers and you quantify how many of them are white and how many of them are purple. And you say like, okay, is this the classical monohybrid cross that you get 3 to 1, the dominant and recessive? So I want that you stop the video and try to answer this question. Are the observed progeny numbers of 73 and 27 consistent with the with a genetic hypothesis that predicts a 3 to 1 ratio, and you need to use the chi-square. So you can stop the video and I will solve it in a second. Okay, so if you already finished, you know the answer, and the first thing that you have to do is to again try to see what is your null hypothesis. Yeah, so the null hypothesis will say that there is no significant difference between the observed and the expected frequencies. On the other case, the alternative hypothesis will say the opposite, that is, there is a statistically significant relationship between these two variables. So the null hypothesis is that the offspring will appear in a ratio of 3 to 4 dominant and in the dominance and 1 to 4 in the recessive. So the purple will be 75%, while this one will be only 25%. So the next step is to apply the formula. So I'm very quickly not going to go step by step, but I'm just going to show you some values. The first thing that as we talk, is to have the observed and expected values. So these will be your observed values, this will be the expected values, and this is a ratio 3 to 1. Then you just have to subtract it, and if you subtract 73 from if you subtract 75 from 73, you get -2, and here if you subtract 25 from 27, you get 2. Then you raise it to the power of 2, you get 4, and then you divide it by this, so you will get these two values. You can double check that in your exercise, and then you add these two values. One is the probability of getting purple flowers, and this one 0.16 is the probability of getting white flowers. You add these two values and you get this is your critical value. Okay, so now let's use the table to calculate. So again, the values here, they will be very similar to the one of the coin. So the first is the degree of freedom. We only have these two alleles that are the purple flowers and the white flowers. So we will have only 1 degree of freedom. So we are using 0.05 as a probability. So we are 95% sure of our results. And here, the intersection of these will give us the critical value. Now we compare this critical value with our chi-square value that we just got. Remember, here it will be 3.8. So if it doesn't exceed the value, you will accept the null hypothesis. On the other hand, if it's higher than 3.8, you will reject the hypothesis. In our case is lower, so we are going to accept the null hypothesis in this case. So we think that those results, although you are not getting the ratio 3 to 1 perfect, they are good enough. And we think that the Mendelian, the inheritance pattern of simple genetics, of the monohybrid cross of a single gene, is enough to answer those results. Okay, now we're going to go to the problem number 3. This will be a slightly more difficult problem. So as I said, this is going to be a little bit more difficult, but you can try by yourself in the beginning. So let's consider this example. You have two pure lines, yeah, and one of them will have yellow petals and the other one will have red petals. And in the F1, all of them are orange. However, when you go to the F2, you get this frequency. A lot of orange and much less yellow and red. So what hypothesis can we propose to explain these results? So will you go and say like, no, this is a Mendelian example, or you will say, no, maybe this could be a different inheritance pattern. Yeah, this could be an example of epistasis. This could be an example of incomplete dominant, multiple alleles. Yeah, so don't worry, you don't have it to you don't need to have it right. You just have to make some hypothesis. So stop the video, think about it, try to solve it, and in a second I will answer it for you. So here they could be two possibilities. Yeah, so they could be an example of incomplete dominance, or this could be an example of epistasis. Yeah, and let's start working with those two hypotheses. Yeah, so we can make a new hypothesis for an incomplete dominance, and then we can see the alternative hypothesis. Yeah, and the other case, it could be we can make a new hypothesis for this, for a recessive epistasis of, and we can try to answer those things. So our parentals in all the cases will be the same. We have yellow, and here we have red, and here in our F1 we get all orange. And our expect values, if this is incomplete dominance, we're going to have half of them will be orange, and half of them, and one and four of them will be yellow, and one four of them will be red. Yeah, so this will be easy the example of incomplete dominance. So this is not, it will be not a Mendelian, the simple Mendelian inheritance. The other one that it could be an example of epistasis. And remember, in epistasis, when you have epistasis, it's slightly more different, more difficult. And in this case, it is a case of epistasis of red, the recessive on Y, and yellow on the Y capital, Y dominant, and so if you get um, this recessive, it will be red. Yeah, so you will have 80 of them will be red. If you get a capital R, you will get, and you get this too, it will be yellow. And if you get a capital R and a capital Y, you get orange. Yeah, so you can see those examples. Yeah, analyze it, and now we're going to test them. So let's start thinking about this. If it's incomplete dominance, so if it's incomplete dominance, the expected values will be 1, 2, 1. Yeah, so 1 for yellow, 2 for orange, and 1 for the red one. So and if we make a Punnett square, this can be a good solution. Yeah, so we have yellow and we have red here, and you get, as there is a complete dominance, this can explain that all of them are orange. Then in the second generation, you get these two with G1, it will be yellow. The one with G2, it will be red, and the one that are heterozygous, these two will be orange. So this in theory makes sense. So now let's try to calculate the values. So we have, these are the observed values: 61, 182, and 72. Okay, and for a total of 320. And now our so these were the observed values, and these are our expected values. Yeah, 80, 160, and 80. So now we can apply the formula, and here you will see the results. So you will get, here you can check how good, how close you were to the data, if there was a mistake. And I think the most important thing here that I wanted to show you is the critical value. Yeah. So we calculate the degrees of freedom, and here look, we have three groups: yellow, orange, and red. So it will be 3 and we subtract 1, so the degrees of freedom will be 2. And again, we want to be 90% sure that to reject the null hypothesis. And now we have to find the critical value. So we go here, it will be 2 in this case because you have this three group: orange, red, and yellow. Now again, we continue in the 95%. So it will be 5.9. And again, we if it doesn't accept the value, we accept the null hypothesis. However, if it exceeds the value, we will then reject the null hypothesis. Here is our critical value, and here we have this 7.6. So in this case, we reject the null hypothesis. So it seems that at least this is not an example of incomplete dominance. Okay, so the data doesn't fit this example. So as I said, incomplete dominance hypothesis must be rejected. Yeah, it's not good enough to be considered an example of incomplete dominance. So now let's try the other example. Okay, so now let's try to test the other hypothesis. Again, I recommend you to stop the video, try to go back and try to start testing the hypothesis. You can go back and see the different values of the epistasis if you have a doubt, and stop the video, and in a second when you're done, we can see if there was a problem or you have any question. So epistasis. So here, this is the data that I previously gave you. So the first thing that I recommend you to do in this exercise that is a little bit more complicated is just try to have the Punnett square. So here they said that when they are heterozygous, yeah, you get orange, yeah, and this explains your F1. Now let's go, so this will be your F1. Now let's try to see what happened when you have your F2. So in your F2, you are crossing the two heterozygous, yeah? And when you're crossing these two heterozygous, you got this value, you get this combination, sorry. And when you get these combinations, you see that here, when you get a dominant homozygous or a heterozygous, you get the orange. So this can explain why you have so much orange. Yeah, a higher probability of orange. When you have the yellow that is homozygous recessive, yeah, the white that is homozygous recessive, sorry, you get yellow, and this is why you have these three. And when you get a red one, an R1, that is the homozygous recessive for R, you get the red one. Yeah. So this can explain relatively well why you have so many orange and why you have much less red and yellow. So now let's try to, all that in theory seems to be correct. Now let's see if statistically the data support our hypothesis. So we have the observed data. Now we have the expected data. And now we apply the formula. And here is the value that we got. If you see, it's very small, so it's very promising. And now we calculate the degrees of freedom. So again, we have three groups, so it will be 2. If we want to apply, we want to be 90% sure to reject the null hypothesis, you're going to take 0.05, and we are going to find the critical values. We generally do it. So 2, 5, and you get 5.91, 5.9, as we got last time. Again, we have the values here, and here we have the phi 91, and here this value will be located in this region, so it will be considered um, for that reason we will as is lower, we will accept the null hypothesis. Yeah, in other words, we conclude that the results uphold the hypothesis of a recessive epistasis. So what I recommend you is to go and try to solve it again, rewatch it. I know I gave a big jump from ones that they were very easy with the coin, then a second one with a simple example of a monohybrid cross, and then I give you uh, some that are more complicated. And one of those can be used for the test. For no, sorry, not for the test. Can be used for the lab report. So try to check it again, and if you have any doubt in class, we can solve more exercises. Okay, have a good day. Bye.